Good evening, linear algebra students. It is Sunday evening for me. It's a little bit dark, but that's it, artificial lighting, and I have to make this video. And you have to watch it and fill the table that is in your lecture notes, which is this one. So here's the example. Given some matrices of the following sizes and rank, fill the missing entries in the following table. And of course, I won't just put the numbers there. I will also give you a couple of reminders on how to fill this. Okay, so first of all, the rank of A, so this thing, okay, you have to remember that this is the dimension of the column space, okay? So rank of A is the dimension of col A, okay? And there's nothing to do with it in the sense that it's here, but we will use it to determine the dimension of the null space of A. And this is because of the rank theorem. Okay, so let's actually fill in the dimension of null A part. Okay, so I'll color code this in red. Okay, and it goes with this theorem. So the number of columns of A is equal the rank of A, so the dimension of the column space that we have over here, plus the dimension of the null space of A. So in other words, to fill that row, what you're going to do is you're going to subtract the rank of A, and actually, let's actually name the number of columns of A to be n. So it means that you're going to write that the dimension of the null space of A is equal n minus the rank of A. Okay? So in other words, you're going to look at the columns. The columns are always like the second part of the size. Okay, so 9, 5, 4, and 2. And you're just going to subtract the rank. So 3 minus 3, 0. Then 3 minus 2, 1. 3 minus 1, 2. 9 minus 2, 7. 5 minus 2, 3. 4 minus 0, 4. And 2 minus 2, 0. Okay? Now keep in mind that if the dimension of the null space of A is 0, it means that it has a lot of important consequences. That the columns of A are linearly independent, that AX equals 0 has only the trivial solution, or you can also say that the null space is the trivial vector space, like the 0 vector, like the trivial subspace of Rn. But let's continue. Okay, let's now talk about the rank of A transpose. So let's color code this in blue, let's say. Okay. So the rank of A transpose is obviously the dimension of col A transpose, col of A transpose. This is what I want to write. And remember that the col A transpose, the column space of A transpose, sorry, is the row space of A. So it's the dimension of row A. Okay? And there's a theorem that we saw in class that I'm not going to prove again, but I'm actually just going to justify. The rank of A transpose is equal to the rank of A. And the reason for that is simply because the dimensions of the row space of A is the number of rows that have a pivot. And the dimension of the column space of A will be the number of columns that have a pivot. Okay? And since the pivot occurs in different rows and in different columns, then automatically there are as many rows that have a pivot than columns that have a pivot. So that's why this theorem is true. So the dimension of the row space of a matrix is the same as the dimension of the column space of a matrix. So in other words, the only thing we need to do is to literally copy paste these numbers here, right? So we're gonna have 3, 2, 1, 2, 2, 0, 2. All right. Now let's finish this. And unfortunately, I wanted orange, but I just have purple. So here we go. We're going to do the dimension of null A transpose. And we're going to do the same thing. So the number of columns, actually, yeah, I'm of A transpose. Now, the number of columns of A transpose, keep in mind, this is the number of rows of A. Okay, so number of rows of A. And this is equal to the rank of A transpose plus the dimension of null A transpose. So rank A transpose plus dimension of null A transpose. There you go. Which is equal to M. So using the same argument, okay, the dimension of the null of A transpose is going to be equal M minus the rank. I'm going to say the rank of A transpose, but keep in mind that the rank of A transpose is the same as the rank of A by this theorem. So from there, you look at the rows now. Okay, so these are the number of rows. And you subtract the rank of A transpose. So 3 minus 3, 0. Then 3 minus 1, 0. 3 minus 2, 1. What did I do? 3 minus 1, 2. Then, okay, here. 5 minus 2, 3. Okay. 9 minus 2, 7. 4 minus 0, 4. And finally, 6 minus 2, 4. Okay. So if you go too fast, you might think, for example, that the dimension of null A and the dimension of null A transpose are the same, but this is only if the matrices are square, right? Because otherwise, as you can see, if you look at these two columns, the dimensions of null A and the dimensions of null A transpose are actually swapped because you're using because in one case you're using the column to determine it, like the dimension of null A, you use the columns, and the dimensions of null A transpose, you're using the rows. So that's why these numbers are not the same for these two columns, sorry. All right, and okay, so I don't know how much I can comment over here. So for the case of a square matrix, if you have a 0 rank, it means that the null space, the dimension of the null space is the maximum possible, which is 4. Here, what we have to comment is if the matrix has maximal rank, then it depends, right? If you're looking, it depends on which has less, like the rows or the columns. So whatever is like, if you have less columns than rows, you will have a dimension of the null space that is 0. But if you have more column than rows, it's going to be the opposite scenario. All right. So I hope this helped. So see you in the next video.